Hi, my name is Jesus Ramirez from Singularity Engineering, and today I am going to explain you how to set up the thin wall model for heat exchange processes. This is the geometry that we are going to use in our simulation. This geometry is composed by four solids. The first one is a solid that will be used as heat source, and from this solid is where the heat is going to be transferred to the other solids. This one is an intermediate solid that will receive the energy from the heat source solid and will transfer it through the other solids that compose the geometry. This one will be prescribed as a fluid, a static fluid. It is going to be a fluid that is not um, with any motion. And this one is the upper solid that is other solid that we have defined here to help us to explain the thin wall model setup. Now we're going to show how is the meshing process. This is a very simple mesh. Then we are not going to extend the explanation in the meshing process. Okay, then we have our four solids. This can be checked here. Then we have our solids. Then we have created a multi-sound method for all the for all solids and with a mapped mesh type of hexa, and the method is a multi-sound method. Also, we have created several name selections in order to facilitate the setup procedure in Fluent. Okay, then we have the header tab. Let me one. Okay, then we have our header tab. Then we have the heater bottom. Okay, and also we have the wall heater. Okay, and also, for example, if I display here, then we have the wafer wall. Okay, that are these walls. Also have the wafer top, and for all solids we did the same procedure to take or to consider the walls in the ANSYS Fluent setup model. Then we are going to mesh, and we are going to show all bodies, and we have here our mesh. It is a very simple mesh. We can view our skewness. It's very low skewness. Then this is a very good mesh, even with it has a few cells. It's more or less it has 95,000 cells approximately. Okay, then right now we are going to the ANSYS Fluent setup, and I will show you how to set up the thin wall model and how does this model influence the results that we obtain in a heat transfer process. Okay, now we are going to perform the setup of the simulation. Then we are going to to perform a steady state simulation. We are going to enable the energy equation, and we are not going to use for this case any turbulence model because the fluid is going to be static. Okay, then it is not required to use a turbulence model. The fluid will be not flowing. Okay, now we have defined air as the fluid material, and also we have defined aluminum and steel. With the steel, we have changed the thermal conductivity in order to see and to magnify the effect of this parameter and the changes on the temperature profiles that we are going to obtain in this example. Then we have one fluid zone that is defined as air. Also, we have three solid cell zones. The first one is the heater, and we have also the intermediate solid that is called wafer, and we have the upper solid, okay, as we show you in the geometry section and in the meshing section. Okay, now we are going to define the boundary conditions. Then we have uh, all boundary conditions were prescribed as of wall because, as I already know, there is not going to be any flowing in this case. Then the idea is that the heater uh, begins to heat uh, to transfer heat through all bodies. Then the heater is here and the heat is going to flow in this direction. Then that's the idea, and the idea is we see how the temperature profile is going to be affected by the use of the thin wall model. Then for this purpose, this boundary condition, that is this one, that is the heater bottom wall, was prescribed with a temperature of 350 Kelvin. Then the other walls, for example, the heater top wall was prescribed as couple because there is an interface among different bodies. Then it's recommended to use the couple. Okay, for example, all all of the boundary conditions for all walls between the heater and the upper solid were prescribed as couple, except the top top wall of this solid. For example, this was prescribed with a temperature of 300 Kelvin. Then we have a temperature gradient among this wall and this other wall that is 350 Kelvin. Then this temperature gradient is which will allow us to generate our heat transfer process in this direction, in the y positive direction. Okay, then as you can see, for example, if we see the wafer top boundary condition is a couple, but here is a very important thing that is related to the thin wall model. You can see here that the wall thickness was prescribed as 0. Then for this case, this boundary condition doesn't have any thickness, then it doesn't have any thermal resistance uh, for the heat transfer process. Then if we let this value as 0, as is already, for example, uh, here, let me see here top, okay, then the thin wall model is not enabled, is not working. Then let's see how this process will be resolved in Fluent and how the temperature profile is going to be um, solved. Then let's run this simulation and see what happens. Once the simulation has finished, we can extract the temperature profile over a line that is located to the geometrical center of our computational domain from the bottom wall of the heater to the top wall of the upper solid. Then we can see that the temperature here that is in the bottom wall of the heater is 350 Kelvin. Then the temperature begins to reduce, and here in this point the heater ends. Then the temperature also reduced, but with a lower um, rate, and this is because the material of the heater is different to the material of the second solid, that is the wafer. This is the steel and this is aluminum. Then we have a subit reduction, a sharp reduction in the velocity profile, and this is because this is the air layer where is located the air, and here is the the rest of the profile where is located the upper solid, which is also aluminum. Then we can see here how the thermal resistance of the material are affecting our the temperature profile. Right now, let's see what happens when the thin wall option is enabled, or we use a thickness different of zero value. Then this this thin wall function can be used, for example, to emulate or to consider the contact thermal resistance among the solids, right? You know that contact resistance is presented when you have the solid in contact, and as the surfaces are not plane ideally plane, they have roughness. Then there is a contact thermal resistance that have to be taken into account in the heat transfer processes. Then one way to do this is to use the thin wall model. Then let's see how we can do it. Then right now, what I'm going to do is to add a thickness to the top wall of the heater. Then let's see here where boundary condition, and I have the heater top wall. Then I'm going to use a wall thickness, and in this case I'm going to use a non-realistic um, wall thickness, only to increase the effect that this model have in the has in the heat transfer process. Then let's say this is, for example, 0.1 meters, and let's see, okay, and let's run the simulation and see what happens with this profile, but now using the thin wall value different from of 0 for the heater top wall. Once the simulation has ended, we can also obtain the temperature profile for the case where the thin wall model was enabled by prescribing a wall thickness for the top wall of the heater. Then you can see the difference on the temperature profile for both cases. This is the case without thin wall model, and this is the case for the uh, where the thin wall model was used. Then, as you can see here in this point, is no defect of the thin wall model, and you can see that is very important. Also, something important to remark is that this point and this point are in the same coordinate, 0.02, that is the height of the heater. And that's it, because the thin wall model is an artificial thickness. It does not include any additional mesh or solid in the wall we are prescribing it. It's just an artificial. Then you have two temperatures. This is the, let's say, the temperature of the hot heater, and here in the other part of the virtual thickness that we impose in the thin wall model. The reduced height here because we use a value of 0.1 meters, that is 5 times the height of the heater. Then that's the reason of this huge difference in temperature. But as you can see here, the use of thin wall allow us to take into account, for example, the effect of the contact thermal resistance when two solids are together, or also if I have two fluids that are going to be separated by a solid sheet, then I can use also the thin wall model. Remember that for using this model, you only have to go to the boundary condition and change the value of the wall thickness. For example, let's see the wafer top wall. Then you change this value, and for a value different for of 0, then you will be taking into account or considering the the thin wall model, and as we show you, as I showed you before, it has an influence on the heat transfer processes and also in the temperature profile. Well, I think this a situation that we can found regularly in our professional life. Then I think it's important to have this concept clear and how to set up the thin wall model for using in our projects. Well, guys, thank you very much for your attention. This was Jesus Ramirez from Singularity Engineering. Thank you very much.